saturable absorption is a property of any material where the absorption of light decreases, saturates with increasing light intensity, or in other words, transmission of light increases with increasing intensity of light passing through it. At sufficiently high intensity of the input beam, ground state population is depleted completely and therefore absorption saturates and the material becomes transparent at high intensity. It is called intensity dependent transparency. Most materials exhibit some saturable absorption, but only at very high optical intensities. Saturable absorber can distinguish a weak and a strong spike in a long pulse. Let's say this is my cavity, the gain medium. I am pumping to create inversion, population inversion, and then I am undergoing stimulated emission in the medium, and at some point of time I have been able to get a very long pulse with this many spikes. What will happen the moment I have created this long pulse? Presence of this saturable absorber in the cavity, it will distinguish the weak spikes and a strong spike. Due to its intensity dependent transparency, it will transmit a strong spike and absorb a weak one. In laser cavity, a long pulse can be generated with weak and strong spikes when modes are not really in phase. Therefore, saturable absorber can select strong spike by transmitting them. If a saturable absorber is placed in the laser cavity, it will transmit only those modes which are in phase and responsible for creation of the strong spike A. All other modes which are not in phase are suppressed because they are contributing to this weak spikes. This idea is shown here. In the first round trip, the laser cavity creates a broad pulse with many spikes, the one which is shown here, and in the next trip, because the spike A having intensity higher than a threshold value, above this threshold value only, saturable absorber will start working, will start transmitting the beam. That's why this portion of the beam, this portion of the pulse will be transmitted, and the moment it is transmitted, it will be intensified in the second round trip by another stimulated emission, and gradually this portion of the pulse will be suppressed. The saturable absorber acts like a in-phase mode selector. The saturable absorber acts like an in-phase mode selector which helps log the modes in the laser cavity. Similar to saturable absorber, in which absorption varies with intensity, mode locking can also be achieved using Kerr effect, in which medium's refractive index varies with intensity. We have already studied optical Kerr effect, which shows that refractive index, that is nonlinear refractive index, depends on the intensity profile. And we know that due to TEM mode, intensity as Kerr effect may arise in the laser gain medium itself, additional optical element like saturable absorber is not required for mode locking, and this is why mode locking This kind of mode locking is called self mode locking. Self mode locking mechanism is very easy to obtain and frequently used for building ultra fast laser oscillator. In this case, the laser gain medium not only lasers but also locks the mode by Carr effect. So, what does it do? According to Carr effect, the refractive index of a medium varies with intensity. And that is why the medium does not feel a homogeneous refractive index as it passes through, as the beam passes through the medium. That is why a beam, a Gaussian beam, does not feel a homogeneous refractive index as it passes through the medium, because its intensity varies along the perpendicular axis of the propagation direction. So, this intensity variation is shown here. It can be varied like this way. I have a beam propagating along this way. So, if I place one piece of paper, then intensity will vary along this way. Now, Carr effects becomes prominent for modes which are in phase due to the resultant high intensity. If I have in phase frequency components, they will produce higher intensity, and that can be focused due to optical Carr effect. And if we use an aperture and a lens, then what might happen if we compare low intensity pulse and high intensity pulses, then this focusing occurs because of the optical Carr effect. This is present only for high intensity pulses. High intensity pulses are created by those modes which are in phase, and then after passing through this aperture, it will make a parallel beam. It will come back again along the same direction, and it will be sustained in the cavity. But think of low intensity pulse where frequency components are not locked, their modes are not locked, and that is why we do not see this lensing effect. In the end, this lens will focus the beam here, and slowly after the reflection it will start diverging the beam. When it will start diverging the beam, it will go out of the cavity. So, this arrangement, this Carr lens and an aperture, can lock the modes which are in phase by selecting them or allowing them to sustain in the cavity. Is mode locking enough to generate ultra fast pulse? So, the first thing we have learned here is that we need many frequency components. Then we have learned that all frequency component will not sustain in the cavity. There are some frequency components which will sustain in the cavity, and those frequency components are called longitudinal modes. But in spite of having many longitudinal modes, we need mode locking technique to produce an ultra fast pulse. And the last component which we need is the dispersion compensation. Previously we have mentioned that when a pulse, even if I have a short pulse, but when it propagates through a medium, every medium is dispersive. That means refractive index changes as a function of, increases as a function of frequency. So, all the frequency components which has constructed this pulse will experience different refractive index, different velocity. That is why they will be stretched. And the moment we have stretched it, I need to have, to produce a short pulse, I need to have a mechanism, and that is called dispersion compensation, to create the short pulse, to get the recompress the broad pulse again to the short pulse. And we have seen that angular dispersion is very useful given by prism. So, this is the pair prism we have used, we can use to compress a stretch pulse by introducing negative GVD. So, we are done. Now, we have all the optical elements which we need for to construct an ultrafast laser. We have this gain medium, Ti-sapphire gain medium. We have optical cavity composed of these two mirrors, CM1 and CM2, and we have output coupler less than 100% reflectivity. This is the output of the beam. Dispersion compensator composed of two prisms, and high reflector which is giving 100% reflectivity, and mode blocking element which includes iris and Ti-sapphire, it is self mode locking, and a pump source. This kind of laser system is called oscillator. Ti-sapphire crystal is pumped by the output of the continuous wave argon laser or diode pump frequency doubled YAG laser. The CW light is focused into the Ti-sapphire crystal collinear with the laser cavity itself. CM1 is a dichroic mirror which is transparent at 500 nanometer and reflects the emission wavelength of Ti-sapphire, which is 800 nanometer. So, within this cavity we have 800 nanometer and pump is 500 nanometer. That we can understand from 4 level system. We have pump which is 500 nanometer higher frequency, and stimulated emission will occur at lower frequency which is 800 nanometer. Mode locking here is achieved through the optical Kerr effect, it is called self mode locking. The generated 800 nanometer light passes through a prism pair and gets reflected by the end mirror, then returns along the same path so that it can pass out of the cavity through the output coupler. Two prisms P1 and P2 compensate for the dispersion of the group velocity inside the cavity. Employing self mode locked Ti-sapphire laser oscillator as depicted here, one can generate pulses as short as 20 femtosecond with excellent stability. To generate pulses less than 10 femtosecond duration, the prism dispersion compensation is not enough. In that case, mirror dispersion compensation is efficient way to generate ultrafast pulses as short as less than 7 femtosecond. Typical output energy of a mode lock oscillator is 5 to 10 nanojoule per pulse. In many applications of ultrafast laser spectroscopy, this energy may be enough, but what about if we need more energy? Then we have to amplify. We will stop here and we will meet again for the same module.